Okay, so here I am. I wanted to talk to you a little bit about coordinate systems and in particular how coordinates work to get you started. When we talk about coordinate systems and what will come further on is be this idea of change of basis. Really want to think about writing the vectors that we know in our standard coordinate systems, x, y, z, for example, in R3, in terms of different coordinates. And so it's kind of like translating between languages. So just as a recap from what you probably have looked at before, let me see here. If you had a vector in R2, say the vector 2, 3, and this vector was in R2, then we know that this means 2 times the standard basis in R2, so 1, 0, plus 3 times 0, 1. And this is how we get that vector 2, 3. And so those coefficients here and here of the standard basis, that's how we write the actual vector 2, 3, and those coefficients are called coordinates. Now you all took a quiz and we talked about this in class, but we know that the coordinates come from an ordered basis. And the basis has to be ordered. That just means that those basis vectors are put in some sort of order because otherwise we'd have no idea what someone really meant when they referenced the vector 2, 3. So just as some notation, since this 2, 3 is written in terms of the standard basis, which is b is equal to 1, 0, 0, 1, and sometimes people will use a semicolon to indicate that the basis is ordered, then since it's in terms of that standard basis, then we just write 2, 3. Now what we'll see later on is that if we wanted to write the vector, say 2, 3, in terms of another basis, c, then this would be the coordinates for a basis c. So I don't know what c consists of. We can make something up, but if c was a basis for R2 that consisted of vectors c1 and c2, then that would mean that the vector 2, 3, if we were to write it in terms of the standard basis, would be whatever we got from 2 times c1 plus 3 times c2. And this would be the vector, we can call it x, in terms of the standard basis. I'll use an S for standard basis this time. So we'll see some of this going on as we go through these slides. All right, so now let's go back. We have our vector in terms of the standard basis, and you see here, this is a vector that's from the origin to a point in space. The point is 0.5, 0.87, and so that's what we call a position vector, and that's written in terms of the standard basis, 1, 0, 0, 1. And just so we can remember from our calculus 3, if we've had that, or some physics class, remember that in this direction there is a unit vector called I hat. That is the vector 1, 0. And then in the y direction, positive y direction, there's a unit vector called j hat, and that unit vector is referred to as 0, 1. All right? So unit vector because it has length 1. And so all of the vectors in R2 that we've normally talked about are written in terms of those two coordinate systems. From your physics days, you may have seen something written like the vector x is equal to x1 I hat plus x2 j hat, right? That's how you typically write them in physics. Okay, great. So now, what if we rotated our coordinate system by pi over 4? So we took the x-axis and y-axis and just shifted them around as that green arc did by 45 degrees. Notice that our green vector is still the same vector, but what if we wanted to write it in terms of what is now x tilde and y tilde? What would that look like? Well, it turns out that that vector goes up the positive x tilde axis 0.69 units, and up the positive y tilde axis 0.19 units. And so in terms of x tilde and y tilde, the vector would be written as 0.69, 0.19. Now, how do we do that? Well, first of all, we realize that x tilde was in the direction of 1, 1. If you look at that, that was just 45 degrees in the first quadrant. And y tilde is in the direction of minus 1, 1. And so the basis now, b, is the ordered basis 1, 1 minus 1, 1. And so the real question in order to find those coordinates is how can we write our vector 0.5, 0.87 in terms of that new basis b? And so we're just asking how do we translate it into the language of b, right? And so we're really looking for a way, and forgive my notation here because I don't want to give you the impression that this is not really x tilde and y tilde here. So it might have been better if I just used generic here, x and y, but you get the idea. So I'm not referring to those vectors there. It's just a bad choice because they mean something different here than they did on the previous slide. But really what I'm trying to figure out are what are the appropriate coordinates x and y so that I can combine the vectors 1, 1 and the vector minus 1, 1 and get 0.5, 0.87. And so I look at a system of equations here. So let me get out of there. And so the system of equations that comes from this is just taking the entries here, as we've done all along, and making them the coefficient matrix. This is the right-hand side b. When I solve, I get that, and of course we call this x and y now, right, just for consistency's sake. The vector xy is equal to 0.69, 0.19. So really changing from one coordinate system to another is nothing more than trying to figure out the appropriate weights necessary to multiply each of the basis vectors so that you get the vector that was in the standard basis. So I hope this helps you a little bit.